Hello, welcome back. We are going to do an example for the Carnot cycle. I'm going to warn you, this one is pretty long. If you'll notice in the note packet, I gave you 2 blank sheets of paper. That's why. Hopefully that will be enough. Hopefully you don't write as large as I do. So bear with me, this one's going to take a while, but this one does give you a really good review of some of the previous concepts we have worked on. So it puts everything together in this one problem. Let's get started. We're going to have 1.5 pounds of water within a piston cylinder assembly. We're going to be having a Carnot power cycle. Now, during the isothermal expansion, our water is going to be heated at a temperature of 500 degrees Fahrenheit from saturated liquid to saturated vapor. The vapor then is going to expand adiabatically to a temperature of 100 degrees Fahrenheit, and we get a quality of 70.38%. We're going to sketch out the PV diagram, look at the work and heat transfer for all of the processes, and we will evaluate thermal efficiency. Before we get started, let's look at this. We're going to have isothermal expansion, where we go from saturated liquid to saturated vapor. Then the vapor is going to expand adiabatically, and then we get this quality. So these things will help us draw the PV diagram. Now let's start out by drawing that diagram. Alright, so we got V and then we've got P here. Now, what we need to do is we need to label our states on here. So our initial state, we have saturated liquid, our temperature is 500. Let's go ahead and draw the dome. It's going to look like that. And now, let's draw the line for the temperature. So this will be TH. We know that because we started at 500, then we're going to drop down to 100. So TH is going to be for 500 degrees Fahrenheit. And we need that in Rankine for when we get to our equations. So let's go ahead and convert that to 960 degrees Rankine. Now that we have that, let's put our states on here. Initially we're at saturated liquid. So where should we put state 1? Hopefully you're thinking right here, because that's where it needs to go. This is the saturated liquid point. This is right before we start to vaporize. Now, state 2, we're going to convert all the way over to saturated vapor. So that means we no longer have any liquid water. We're all vapor. So that'll be state 2. And then let's draw an arrow. We're going from 1 to 2. And last thing I want to put on here is, let's go ahead and label the pressure that we are at while we're going from 1 to 2. To find that, we're going to use the saturated water table. So we're going to look up our temperature, which is 500 degrees, and then we will find the pressure. So here's our table. This is the saturated water table. This is A2E is the table number. 500, you have a pressure of 680. So 680 is the saturation pressure. So let's just put that over here, and this is PSI. Alright, so now we got 680. After that, we are told that the vapor is then going to expand adiabatically to a temperature of 100, and then it gives us that quality. Let's draw another line for the temperature. This will be TC. This is our lower temperature, which is 100 degrees. Convert that to Rankine, you get 560 degrees Rankine. And we know our quality is 70.38%. If our quality was 100%, we'd be right here at this intersection. But we're not quite there, so we're going to put it over to the left a little bit. And I'll just put it right here. So now we're going to go that way. All right. And if you drew this dome a little bit better, you wouldn't have it look like it's straight below here. So 70% should really be over more to the left, but I don't want to make my drawing look odd, so I just put it down there. Okay, so now we've got that, and let's label the quality here. So X is 70.38% at that point. Now remember, at this point we are at 100 degrees Fahrenheit. Let's go ahead and find our pressure. So go to your saturated water table and look up 100. Now look at our pressure. It's a lot lower, 0.9503. That's way lower than what we had up here at 680. Okay, so label that pressure. Now that's all the information it really gave us. Okay, now we know that this first one we were told that we had isothermal expansion. So this process here is isothermal. Now here we are going to have the adiabatic process. So we've got that. It's a B there. That means this next process going from 3 to 4, this is also going to be isothermal. And we weren't really given any information for 4, so I'm just going to put 4 right here. And I know we're going from 3 to 4, so the arrow goes to the left, and then we're going to go from 4 back up to 1. And then going from 4 to 1, that's going to be adiabatic also. Okay, so that's going to be the PV diagram. It's kind of got all of our information that we know on there. Now we're going to go through and we're going to look at each one of these processes, and we're going to find the work and heat transfer for each one. So that's what's going to take quite a bit of time on here. So let's get started. If I can separate the pages here, they're all stuck together. There we go. Alright, so this is for part B. We're going to do process 1 to 2 first. Now remember on here, we've got a volume change. So remember way back we had the equation where work was equal to the integral of pressure times dV. Alright, now if volume is equal to mass times specific volume, you could rewrite this and put it in terms of specific volume, and then what you're going to get is you'll get work of process 1, 2 is going to be the pressure times the mass times specific volume at state 2 minus specific volume of state 1. And we did that in a couple of the examples back in chapter 2, I believe. All right, so in order to find this, we need to find these V numbers. So let's go ahead and do that. We're also going to go ahead and list the specific internal energy numbers because we're going to need them in just a second. So we'll list both of them. So let's just put find V values. Now for the first one, we know we have saturated liquid. That's what we drew in the PV diagram because that's what we were given. That means V1 is going to be the VF number for our given set of conditions. So if you go into table A-2E, you can look up the temperature, which is 500, and you can get VF. Here's 500, work your way over. This one is VF, so it's 0.02043. We need that number. And we also need U1 or UF for 1, so because we're going to need it later. That one's going to be 485.1. So let's write both of those numbers down. And units will be cubic feet per pound. And then U1 is UF, so we're going to have 485.1. That one's in BTU per pound. Now we do the same thing for V2. Now V2, remember we had saturated vapor. That means we're going to look at the saturated vapor value for a specific volume. and you're going to go to your temperature, which is going to be 100. Actually, not 100, sorry about that. It's still going to be 500. So now, here's 500. Look for the G term. So we have 0.6761. And then we need the internal energy. That's 1117.4. So let's write both of those numbers down. Right, so V was a 0.6761. It's cubic feet per pound. And then for U2, we got 1117.4 BTU per pound. Now we've got all of that. That's enough to plug in everything and get our work. We have our pressure, we have our mass, now we have these two specific volumes. So we are good to go with all of that. Let's plug everything in. We're going to have 680 psi times, let's convert over to feet, squared. So we have 144 inches squared per foot squared, times the mass, which is 1.5 pounds, and then multiply by this difference in specific volume. That's 0.6761 minus 0.02043. Those are both cubic feet per pound. Now let's look at all of our units. Inches goes away, pounds goes away, and we need this to be in BTU. All right, so for BTU, what we need to do is convert. We're going to have BTU per 778 foot-pound force. That's our conversion. So now if you look at your units, this is going to take care of the cubic feet because this goes with this. And then pound force goes away, leaving us with BTU. So work for process 1-2 is a positive 123.79 BTU. All right. So now we've got that. Remember, this is a positive value, so work, you can send it out. You can have a transfer of energy due to work out to the surroundings. Now that we got that done, now we got to find Q. Now how should we find Q? What do y'all think? Well, we have one equation that has work and Q in it, and that is our energy balance equation. Now at this point you have to figure out which energy balance equation you want to use. Do you want to use the original one we started out with in the class, or do you want to use the one with all of the mass flow rates? Which one do you think? We want to use the original one, right? Because this is a closed system. This is a piston cylinder assembly. We don't have any mass flow, fortunately, so we get to go back to that simple energy balance equation. So let's put find Q using energy balance. All right, and our equation for that will give us Q12 minus work, process 1-2, that's going to equal M times U2 minus U1. And we're ignoring kinetic and potential energy, so I'm not even going to write them down. Now we have everything we need for this equation. Q12 will be what is unknown. So we're going to have Q12, this is a minus 123.79 BTU equals 1.5 pounds times 1117.4 BTU per pound minus 485.1 BTU per pound. Check out your units. That looks good. Everything's in BTU, so that's perfect. That's what we want. Now our heat transfer term Q for process 1-2 ends up being 1072.24 BTU. Okay, So this is greater than 0, so that means heat transfers to the system. All right, so that's process 1, 2. We still got 3 more of these to go. This is why I warned you it's a long problem. Whoops. We might have to cut the video in half and then do the second half in the next video. All right, so process 2, 3. Remember process 2, 3, if we get our picture back again, that's this process. This one is adiabatic. So what does that tell us about Q? That's right, Q is going to be 0. That was easy. Why can't they all be that easy, right? So Q23 is equal to 0. Perfect. Now we just have to find work. Let's go ahead and do our energy balance equation here. And that'll be Q minus W equals the mass times U3 minus U2. Now, we already said Q was 0, so get rid of that. Now we just need to find these internal energy values. So let's look those up. U2, we already found that up right here. So we can just recopy that number. That was convenient. And then U3, what about U3? We don't have that yet. We were given a quality though. If we're given a quality, that means we're going to have to use this equation where we use the saturated liquid and saturated vapor values. U3 then is going to be UF for state 3 plus the quality at state 3 times UG minus UF. These are going to have to come from the table. At this point, we've got that two-phase mixture. Our temperature is 100 degrees. Let's write down state 3, so two-phase mixture at 100 degrees. This is not Celsius, it's Fahrenheit. Now you'll just look up the 100 degrees in the saturated liquid table, and then you can write down your UF and UG values. So if we go over here to that table, here's our table. Here's 100. Just go over to the right until we get to UF, which is 68.04. And then for the G term, we're going to have 1043.5. These are both BTU per pound. Let's write those down. And this one was 1043.5 BTU per pound. And again, remember this is going to be table A2E. All right. Same place we got those other values from before. Now that we have this, we can plug these in to this equation and we can solve for U3. Let's call this equation 1. So U3 will be 68.04 BTU per pound plus the quality. We don't want to put it in percent form, change that over to decimal form. So that's 0.7038. Multiply that by the difference between these two specific internal energies. So that's 1043.5 minus 68.04. Those are both BTU per pound. And now we can go ahead and do the calculations to get U3. And that'll give us 754.57. And that's BTU per pound. So now we got that. Okay, now we're ready to go back to this energy balance equation right here. We got U2, we got U3, we got our mass, so we can solve for work. So we'll have negative W23 equals 1.5 pounds times 754.57 BTU per pound minus 1117.4 BTU per pound. Calculate all that out, you'll get 544.245 BTU per pound. Here's another answer. We're just moving along, right? It's only taken us 20 minutes so far. Look at your sign, we got positive. So this means work is done by the system. All right, we did not need any sort of external work to be done for us. Now we got 2 more processes to go. We got to go from 3 to 4 and then 4 to 1. Okay, so let's get started on that next one. Now, for state 4, we don't really know anything about that except for the temperature. Our temperature is 100. That's really all that we really know. Let's make a note about that. We don't know anything about state 4 except for the temperature. So at least we know the temperature, right? Now, what we're going to do here is we're going to use an equation we talked about recently. We're going to use the equation QC over QH equals TC over TH. And you might ask, well, why are we using that? Where did that come from? When we talked about reversible cycles, we had this equation. Remember we said we had this relationship? Now, the Carnot cycle is a reversible cycle. Remember, this is kind of like a theoretical best case scenario type thing. So since the Carnot cycle is reversible and this equation here was for reversible cycles, we can use this relationship. And let's make a note about that. We'll just put was developed for reversible cycles. And this one is reversible. All right. Now, at least this gives us another equation. So we've got our TC, we know our TH, and now we can go ahead and solve. We need QC. Let's solve that equation for QC. QC is going to be TC over TH times QH. Now you might be looking at that thinking, okay, I got that we have the temperatures, but what is this QH? QH is going to be the energy transfer you had when you were dealing with that hot reservoir. So if you look at your picture here, this is our temperature line for our hot reservoir. And we already found Q for this process going from 1 to 2. So QH is going to be the Q value we found from 1 to 2. All right. So that value was 1072.24. Now we'll plug in our numbers. So we got 560 over 960, multiply it by 1072.24 BTU. Okay, so remember this was the heat brought into the system. For process 1, 2. Now that we've got this, we can find QC. And you get 625.47 BTU. All right, so this equation here is essentially going to give you just the magnitude. We need to look at the actual sign. This is going to be energy that's discharged. So energy by heat that's discharged to that cold reservoir. So we need to make this a negative value. So Q34 is going to be negative 625.47 BTU. And let's write a note. So it's negative because that heat energy is being discharged, so it's leaving the system. All right, so now we got that. What else do we need here? We need work. Can't forget work. Now if we look at our energy balance equation, we got Q34 minus work for process 3-4. It's going to equal the mass times U4 minus U3. All right, so we don't know anything about U4 yet, so let's go ahead and find work first. And then we'll get an equation for that and we'll work through it, and then eventually we'll be able to solve this. So our work equation for this process is going to be pressure times the mass times V4 minus V3. And this is the same equation essentially that we had when we were going from state 1 to state 2. So if you look back in your notes, when we first started part B, we had this equation. This is the same type of process going on right now. We're at a different temperature, but otherwise this process is still the same type, so we're going to use this equation here. We just changed the states that we are looking at. Now we've got that, let's go ahead and we're going to plug this into here. So we'll write Q34 minus pressure times mass times V4 minus V3. That's going to equal the mass times U4 minus U3. Now, if we look at that, let's go ahead and get Q3 by itself. We'll move all this other stuff over, and then we will expand this and rewrite it in a different form. Q34 then is going to be the mass times the pressure times V4 minus the mass times the pressure times V3 plus the mass times U4 minus the mass times U3. Now, if you look at this equation and look at just the like state terms, so let's look at the 3 subscripts. We have mass times U3, and then we have mass times PV3. Now, if you remember back, we talked about enthalpy, and enthalpy, remember, is U plus P times V. Now, because of this, let's go ahead and rewrite this equation. And we'll group up our like state terms. So Q34 is going to be negative M times U3 plus PV3 plus the mass, again, times U4 plus PV4. So we just restructured this equation. That's all we've done here. But now we have H's, right? We have enthalpies right here. So we can simplify this equation and just put that Q is equal to mass times H4 minus H3. Now what we're going to do, I warned you guys this was a long problem. What we're going to do now is let's go ahead and solve for H4, because we don't have any information about 4 other than the temperature. So let's solve this for H4. And if we do that, we get Q34 over the mass plus H3. And these values we have, right? So we know all of those. So let's go ahead and fill those in. let's plug in our numbers. So for Q34, we had the negative 625.47. That was BTU. Our mass is 1.5 pounds. And then H3. You're going to have to find H3. Remember when we found, let's go back to this page. When we found U3, we used this equation. Remember there's a similar equation for H3. So you're going to use that. So you can take your quality and then use that similar equation to find H3. So we'll just write it in here. So it's HF3 plus X3 times HG3 minus HF3, like that. Now what this is going to give you here, let's see. Now if we look these values up in the table, this one is 68.05. Remember we're just at a temperature of 100 degrees Fahrenheit, so you just look that up. X in decimal form is 0.7038, and then this number here is in the table. That's the 1037. And these are all BTU per pound. So the units for this matches this. So that's all good. Now what you get then for H3 is 797.891. So that's what you get when you plug these numbers in. Alright, so then take that number, add it to this term, and then you'll get H4. So H4 is going to be 380.92. That's BTU per pound. So that's our enthalpy there. Now at this point, we've got a few of the things that we need. We now have H4. We've got our temperature at 4, and since we know the temperature, we also have the pressure. Oops, let's write a note about that. So we've got these 3 things, and remember what we're looking for is work. That's what we're trying to find here. So we need W34. And we know that W34 is equal to pressure times mass times V4 minus V3. All right, now what we're going to need to do is go through and then fill out the rest of this equation. We've got pressure, we've got mass. We can go through and find V3. Same way we did enthalpy. And then we can get V4. So let's go ahead and do that. So V3 first. You're just going to use that same equation that we had before. So VF plus the X times VG minus VF for state 3. So you just look up the values in that table for 100 degrees. And then you'll be able to find V3. If you do that, just to save time, I'm just going to write the number out. You get 246.33 cubic feet per pound. V4, we're going to have VF for 4 plus X4, VG4 minus VF4. Now we can find the VF and VG because we know the temperature. All right, so we know that. We don't know the quality though. We're going to have to find this quality. Alright, so let's do that next. Oh, I've used up all my paper. I've got to find the paper. Okay, so let's go to this sheet of paper. Alright, so to find X4, what we're going to do is let's go ahead and look at our enthalpy equation. We know H4 has got to be equal to HF plus X4 times the HG minus HF. Right, we know that. We can find these H values because we know the temperature. So H4 we said was 380.92, and that's BTU per pound. That's got to equal 68.05. That's what you get for HF at 100 degrees. And then we're going to have plus X4 times the difference between G and F, which is 1037.0 BTU per pound. From this, you can solve for X4. So 0.3017. All right, we're almost to work, I promise you. Then I think we'll stop this video and we'll pick it up the rest of the problem in the next one. All right, so this is our quality. So we've gone from 70% roughly down to 30% vapor. Now, from our V4 equation, we can find V4, and VF is going to be 0.01613. That's cubic feet per pound, plus the quality, 0.3017, and then times VG, which was 350, and then minus the VF term again. So 0.01613 cubic feet per pound. All right, so remember that's VF, that's X, that's VG, that's VF. Now we get V4, 105.61 cubic feet per pound. Finally, we can solve for work. You probably thought we would never get there. If you're still with me, thank you. I know it's a long problem, but it is a good review problem. Let's go ahead and add in all of our numbers. Pressure, we know, is 0.9503. Units are PSI. Mass is 1.5 pounds. And now we have V4 minus V3. Plug in those numbers. 105.61 cubic feet per pound minus V3, which was 246.33. That's cubic feet per pound. And we need it in BTUs, so let's go ahead and convert over. We've got inches over here, we need to get rid of that. So multiply by 144 inches squared per foot squared, and then convert to BTU. So BTU per 778 pound force foot. Okay, there we go. Now, what we get now is BTUs, that'll be our units, because all this other stuff goes away if you work through it all. And that foot multiplied with that gives you cubic feet, which cancels that. So units look good. Finally, let's get this value. So that's going to be negative 37.13 BTU. This is less than 0. That means work is done on the system. So you had to have some sort of power supply or something happening in order to make this process happen. Not just going to happen on its own there. All right, and then let's actually, this next part is short, so let's just go ahead and do it in this video, even though we're almost to 40 minutes here. Process 4.1. So for here, we're going from 4 to 1. This is going to be adiabatic, since it's opposite of this one. This one was adiabatic, so this one has to be adiabatic. So Q for this one is 0. Wish they were all that short. Would be amazing. There we go. Now we need to find the work. Go to your energy balance. Q minus work equals mass times U4 minus U1. We already know what U1 is. It's 485.1 BTU per pound. That's from the table. Remember, this was at 500 degrees. Now all we need to do is find U4. And to do that, we're going to look at enthalpy. So H4 is going to equal U4 plus P times V4. And H4, we already found that value was 380.92 BTU per pound. That then needs to equal U4 plus 0.9503 PSI. Multiply that by V4. So 105.61 cubic feet per pound. And then do all your conversions as usual. Get rid of these square inches, or yeah, that's right. So we're getting rid of square inches here. And then we need to convert over to BTU. So divide by 778 foot-pound force. Okay, so if you do all of this, your only unknown here is U4. Solve for that. And we get 362.34. That's BTU per pound. Let's circle. Oh, actually, we don't need to circle that. That's not our answer. I'm getting excited here. We're almost done because this is a lengthy problem. Now that we have this, let's plug it in here. Remember, this Q went to 0. So negative work for process 4 to 1 is going to be 1.5 pounds times 362.34. This is BTU per pound. And then subtract 485.11 BTU per pound. Now that's going to give you negative 184.16 BTU. And this is negative, so work's done on the system. All right, we finally found the work. All right, we've gotten to 42 minutes here. That's pretty long. So let's stop this video here, and I will see you guys next time.